The modern world runs on portable energy, packed into lightweight cells that power everything from smartphones to electric vehicles. Yet, the foundational spark of this revolution was not struck in a Silicon Valley garage or an advanced electronics factory. Instead, the rechargeable lithium battery was born inside the corporate research laboratories of Exxon, the largest oil company on Earth, during an era when petroleum seemed untouchable. In the early 1970s, a severe oil embargo exposed the extreme vulnerability of global energy supply chains. Fearing that fossil fuel reserves might peak or become politically inaccessible, Exxon decided to invest heavily in fundamental scientific research. The corporate mandate was astonishingly broad. Explore alternative energy systems that could secure the company's future beyond petroleum, regardless of how radical those concepts might initially appear. Among the brilliant minds recruited to lead this effort was M. Stanley Whittingham, a young British chemist working at Exxon Research in New Jersey. Whittingham was fascinated by the atomic behavior of solid materials, specifically how small atoms could wedge themselves between the crystal layers of host compounds. He recognized that harnessing these atomic movements could offer an entirely new method for storing chemical energy. To understand Whittingham's breakthrough, we must first examine intercalation, a process where ions reversibly slide into the microscopic gaps of a host material's crystal lattice without destroying its underlying structural framework. Think of it as slipping books into a bookshelf without dismantling the shelves themselves. When the ions enter or leave, the physical structure remains robust, allowing chemical reactions to repeat hundreds of times. Whittingham selected titanium disulfide as his primary host material. Titanium disulfide possesses a layered, sheet-like crystal structure bound together by weak atomic forces, creating perfect microscopic channels for lightweight, positively charged ions. By pairing this compound with pure lithium metal as the negative electrode, Whittingham created an electrochemical system with unmatched chemical potential and extraordinary energy storage capability. By 1976, this research culminated in a monumental breakthrough. Whittingham and his team built the world's first functional, room-temperature rechargeable lithium battery. The experimental cell demonstrated unprecedented energy density for its era, generating an electric potential of approximately 2.2 volts. Exxon immediately patented the technology and began producing small, button cell batteries for consumer field tests, signaling a major leap forward for energy science. The theoretical density of this early system was breathtaking, storing far more energy per unit of weight than traditional lead-acid or nickel-cadmium batteries. Lithium, being the lightest metal on the periodic table and possessing a powerful tendency to yield electrons, offered a dramatic performance advantage. Scientists realized that portable energy could finally be concentrated into compact, highly efficient hardware packages. However, a serious engineering flaw soon threatened to derail the entire innovation. During repeated charge cycles, metallic lithium did not deposit smoothly back onto the negative electrode. Instead, it formed microscopic needle-like crystalline spikes known as dendrites. These jagged tendrils grew relentlessly across the liquid electrolyte until they pierced the thin separator dividing the battery's two sides. When a dendrite pierced the separator, it triggered an internal short circuit, releasing the battery's stored chemical energy instantaneously in an intense burst of heat. The volatile organic electrolyte rapidly ignited, causing small fires and thermal runaway events within the laboratory. These dangerous safety risks made commercial expansion with pure lithium metal electrodes extraordinarily hazardous and commercially unviable. As the 1970s drew to a close, the global economic landscape shifted dramatically. Oil prices stabilized, easing immediate fears of a fossil fuel collapse, and Exxon faced mounting financial pressures across its core petroleum operations. Concluding that battery commercialization was too far removed from its primary business, the company scaled back its research programs and eventually licensed its core patents to outside entities. While corporate backing faltered, the fundamental science lived on in academic laboratories across the world. The theoretical framework established by Whittingham had proved that intercalation was viable. Now, researchers needed to find materials that could withstand higher voltages and eliminate the hazards of pure metallic lithium. The search for a safer, more stable electrochemistry shifted to university physics departments. At the University of Oxford, American physicist John Goodenough recognized that Whittingham's cathode could be fundamentally improved to double its energy output. Goodenough reasoned that substituting metal sulfides with metal oxides would allow the cathode to pull electrons with far greater chemical force. Metal oxides offered a tightly bound crystal structure capable of operating at significantly higher electrical potentials. In 1980, Goodenough achieved his own breakthrough by developing a cathode material made of lithium cobalt oxide. This new compound allowed lithium ions to enter and exit its atomic framework at a cell potential of nearly 4.0 volts, almost double the voltage of Whittingham's design. This dramatic increase in energy density laid the chemical foundation for modern high-performance battery systems. Goodenough's discovery proved that an oxide host material could safely store and release massive amounts of energy without collapsing. Extracting lithium ions left the layered cobalt oxide structure intact, creating a remarkably stable host framework. Yet despite this massive leap forward in voltage, the system still relied on unstable pure lithium metal anodes, leaving the severe risk of dendrite formation unresolved. The final piece of the puzzle was solved in Japan during the mid-1980s by researcher Akira Yoshino. Yoshino realized that to make the technology safe for consumer products, pure lithium metal had to be completely eliminated from the battery. Instead of metallic lithium, he sought a secondary intercalation material capable of holding lithium ions safely on the negative electrode side. Yoshino discovered that a carbonaceous material derived from petroleum refining, known as petroleum coke, possessed a porous atomic structure ideal for hosting lithium ions. By pairing Goodenough's lithium cobalt oxide cathode with a carbon-based anode, Yoshino built a battery where lithium existed entirely in ion form, moving back and forth between two host lattices without ever reverting to volatile metallic lithium. This design gave birth to the modern lithium-ion battery, eliminating metallic dendrites and creating a highly stable, repeatable, and safe energy storage device. In 1991, commercial production began, sparking an explosive wave of consumer electronics innovation. Portable computers, cellular phones, and handheld video devices suddenly became smaller, lighter, and far more powerful than previously thought possible. The shift from primary, single-use batteries to high-capacity secondary storage transformed society's relationship with technology. Devices were no longer tethered to wall outlets or restricted by heavy, short-lived power sources. The microscopic dance of lithium ions shuttling between atomic hosts silently powered the digital age, reshaping global communication, commerce, and personal mobility within 2 decades. Looking back, the narrative carries a profound sense of historical irony. The technology that now enables the global transition toward renewable energy and electric vehicles was conceived, funded, and patented by an oil enterprise seeking to hedge against a petroleum crisis. Exxon's early corporate research inadvertently planted the seed for a technology that would one day challenge oil's monopoly on transportation. As battery technology scaled up from small consumer electronics to massive battery packs, electric vehicles emerged as a viable alternative to internal combustion engines. Grid-scale storage facilities began utilizing lithium-ion chemistry to buffer variable wind and solar power. demonstrating that the microscopic atomic physics pioneered in the 1970s could stabilize national power grids. In 2019, M. Stanley Whittingham, John Goodenough, and Akira Yoshino were jointly awarded the Nobel Prize in Chemistry for their sequential breakthroughs. The Nobel Committee recognized that their collective work had created a rechargeable world, laying the technological foundation for a fossil fuel-free society. It was a formal acknowledgement of a journey that began almost half a century earlier. The development of the lithium-ion battery demonstrates how fundamental scientific inquiry can yield consequences far beyond its original intent. A project started inside an oil laboratory to solve an immediate energy threat ultimately triggered a multi-decade cascade of chemical innovations, transforming global industry and environmental engineering in ways no single corporate board could have anticipated. The early architectures pioneered by Whittingham and perfected by Goodenough and Yoshino remain the gold standard of energy storage today. Millions of lithium ions continue to shuttle between layered atomic sheets inside billions of devices every second, silently maintaining the pulse of modern life. It is a quiet, ongoing reaction that traces its lineage directly back to a corporate laboratory in 1976. Ultimately, the story of the lithium-ion battery reminds us that transformative technological revolutions often spring from unexpected origins. What began as a speculative research project within a fossil fuel giant became the defining power source of the 21st century, proving that true scientific genesis frequently lies hidden where we least expect it.